So today we are looking at lesson 3-4. We're looking at rational exponents, properties of rational exponents. That would be exponents that are fractions. So, for example, if the nth root of b is a real number and m is an integer, then b to the 1 over n is equal to the nth root of b. So essentially, the base is the base underneath the radical, and then when you have a fractional exponent, the denominator of that fraction is the index, and this numerator is what this base is raised to. So if you cover up that denominator, you can see it looks like b to the first, and there's b to the first underneath here. Same thing here, if you have b raised to something other than 1 over n, if you cover up this n, because the n is the index, if you cover up the n, you have b to the m as in Mary underneath here. This could also be written in this form. In other words, this m that the base is raised to could be raised to the outside. So let's put some real numbers to this. So for example, the square root of 49 could be written in exponential form as the base 49 remains the base of the exponential form, and then the index here is 2, so it's going to go on the denominator of this fraction. So I've got some fractional exponent here, and the denominator is 2 because the index here is 2, and then 49 is raised to the first power, so there's going to be a 1 here. So it's 49 to the 1/2. Well, what if the numerator in the fractional exponent is not 1? So what if we had instead x to the 3/5? So that's going to equal some radical. So this is our exponential form, this is our radical form. So the denominator is going to go here as the index. So my index is 5. And then cover up that index, you've got x to the 3rd, so x to the 3rd comes underneath here. So again, instead of this 3rd being here, it could be around the whole outside. So you could write it as an or the 5th root of x, and then it could be raised to the 3rd power. That's a 3. All right, so then we've already gone over a lot of these properties in a previous lesson, so I'm just going to zip through all of these here. I'm going to give you some real number examples here. So when multiplying like bases, we add the exponents. So for instance, if I had x to the 4th times x to the 5th, we would add those exponents, and we would get x to the 9th. If I have a power raised to a power, we're going to multiply those exponents. So I might have x to the 4th raised to the 5th. That's going to be x to the 4 times 5, which would be x to the 20th. I could also have multiple things in here raised to that power, and so long as there's no addition or subtraction signs, then we're just going to distribute that power to every exponent you see there. So for instance, I might have 2x inside parentheses raised to the 3rd power. So remember, technically the exponent of these are 1 if you can't see them. And so we're just going to multiply the 3 to the 1 and the 3 to the 1. So we end up with 2 to the 3rd, x to the 3rd, and you have to actually multiply out 2 to the 3rd, which is 8. So you get 8x to the 3rd. And then of course we know that if we have a negative exponent, we're going to put it in the opposite direction. So in this case, it would be going in the denominator. So we might have 2 to the negative 3. So I'm immediately going to put this over 1. And I'm going to take this whole power and move it into the denominator. So I get 2 to the 3rd power in the denominator. If nothing's left in the numerator, you're going to have a 1, and then you have to multiply out 2 to the 3rd, which is 8. So 1 over 8. If we are dividing like bases, we are going to subtract the exponents, and you subtract where there are more. So if I had x to the 5th divided by x squared, there are more x's in the numerator, so all of these are going to subtract with 2 of those. So you end up with x to the 3rd, and there's a 1 left in the denominator, so we don't write it over 1. And finally, remember, if you have a fraction raised to a power, you have to raise the numerator and the denominator to that same power. So for instance, if I had 2 over x raised to the 3rd, don't forget that that's 2 to the 1st and x to the 1st. Power to power, we're going to multiply. So we end up with 2 to the 3rd over x to the 3rd, and you have to raise that 2 to the 3rd, so it's 8 over x to the 3rd. All right. So then we have some problems involving fractional exponents, and so I'm going to make these bigger so that we can see what's going on, but we're going to put them in their fully simplified form. Now there's always more than one way to approach these. So I'm going to try to approach them, in a different way if I think about it. But for right now, I cannot multiply these two because they're not like bases. But I can convert this into its radical form and this into its radical form. Notice that they both have the same index, so they're going to be underneath the same radical. So I get the square root of times the square root of. And the reason why I say square root is because both indexes have a 2. So I know that this is going to be a square root here. So then I'm going to put the 3, if it cover this up, I've got 3 to the 1st. So I'm going to put 3 to the 1st underneath here. And if I cover this up, I have 12 to the 1st, and so that's going to go underneath here. And so now that I have like radicals, I can multiply what's underneath the radical. Now normally I don't multiply these together, but I'm going to because 3 times 12 is 36, and we know that that's a perfect square. And then we end up with a final answer of 6. All right, let's look at B. So now B you can do 2 different ways. So I can take and I can convert 64 into its root form. So it's got a cube root, and 64 is going to be raised to the 1st. So right, 64 to the 1st, and that's a cube root. So this can be converted to the cube root of 64 to the 1st. So 64 you can break into 3 fours. How do I know that? Because I used factor trees. Or you can stretch out, because sometimes this is starting to get a little long. You can stretch out all of its prime numbers. Okay, so because I have a cube root, I want to find a group of 3. So I found one group of 3. So I end up with a 4. Here I've got one group of 3, so I'm going to have a 2, and a second group of 3, so I get another 2, which equals 4. So no matter how you broke apart 64, whether it was into 3 4s or into 6 2s, your final answer turned out to be 4. Now, here's an alternative solution I want you to start to think about. I could actually take 64, and if I prime factored it using prime factor trees, I could break it down into 6 2s, right? So instead of doing all of that, I could have instead, so this is way 2, I could have instead taken 64 and replaced it with 2 to the 6. But remember, 64 is being raised to the 1/3 power. So I could instead use the power to power rule and just multiply these together. So I am going to do this out the long way so you can see what I'm doing, but I'm basically taking 6 and multiplying it to 1/3. 6 times 1/3 is 2. 2 squared is 4. So there's an alternative method. I actually like this method better because this starts to get really long. So I'm going to try to break you of this habit and move you into doing this. But I'll continue to do it both ways. All right, let's look at C. So C, I already see here I have a 4 and a 64. Now I know that I can convert 64 into a base of 4. Or I can convert both of these into bases of 2s, and I can do it way 2 like we just did previously. Or I can put these both into their 4th roots because they both have a denominator here of 4. So let's start with that way first. So 4 to the 1/4 is going to be the 4th root of 4 to the 1st. Again, if you cover this up, I have 4 to the 1st, which goes underneath, and that 4 there is my root, times I've got the 4th root of 64. So that index goes here. The denominator here is the index. And if I cover that up, I have 64 to the 1st, which is going underneath here. So then at this point, both of these are underneath the same radical, so you can multiply them together. Well, that's too big of a number to multiply. So instead, I'm going to either break it down to 4s, so this is my first 4 here. And then remember, previously 64 is 4 to the 3rd, so this is 3 more 4s. So this is your 64 times your 4. And we're looking for a group of 4. So since I'm looking for a group of 4, I get one group of 4, and so this is going to equal 4. If you wanted to break it down into all of its 2's, I've got the 4th root of 4 is 2 times 2, and 64 is 6 2's. Okay, so then I'm looking for groups of 4. So here's one group of 4, which means I have a 2 out in front, and then another group of 4, which means I have another 2, which 2 times 2 is still 4. So both of those get you the same answer. Then I want you to think of it this way. Couldn't I break? Now I could break 64 into 4 to the 3rd, which would actually be the easiest, but since we're starting this out, let's go ahead and break this down to its prime form. 4 is 2 squared. So this is way 2. So 4 is 2 squared, and I'm going to raise that to the 1/4. Why? Because that's what the problem says. So 4 is 2 squared raised to the 1/4 times 64 is 2 to the 6th, and it's raised to the 1/4. So 64 is 2 to the 6th, and it's raised to the 1/4. So now I got a power to a power, power to a power. I'm going to multiply the exponents. So if I multiply 2 times 1/4, I get 2 over 4, which is 1/2. So I get 2 to the 1/2 times, and then if I multiply 64 or 6 to 1/4, I get 6/4, and 6/4 reduces to 3/2. Now the reason for this was because I was trying to get like bases, because I know if I have like bases, then I can add their exponents. So essentially, I'm going to add the 1/2 to the 3/2. Well, that gives me, I have like denominators, so that gives me 2 to the 4/2, which is 2 squared, which is 4. Now I put a lot of work in there that I normally wouldn't put in there, just so that you could see the process and see all of the pieces. All right, let's try D. Now D has a base of 32, and it's got, if I convert this to its radical form, it's got an index of 5. So if I cover that up, underneath the radical, I'm going to have negative 32 in parentheses, keep it in parentheses, and raise it to the 3rd power. So the 5th root of negative 32 to the 3rd. So the 5th root one here, and cover that up, negative 32 to the 3rd is underneath here. Now you could put this 3rd on the outside if you want to, and that's fine. But I'm going to convert 32 to a base of 2. So I want you to start to think in terms of a base of 2. So I have the 5th root. 32 is 5 2's. Well, because it's negative, I've got 5 negative 2's. Whoops, hang on. I need to No, I want to have that there. So I've got 5 -2s, so it's going to look a little funky. So I have 5 -2s, but then, because that's just your -32, so then I'm going to raise all of that to the third power. So why did I do this? I have 32. Right here is 32, -2 to the fifth, raised to the third. Now I have a power to a power. So that means that I've got the fifth root, power to power, you multiply exponents, so I have -2. 5 times 3 is 15. And so now I can use my index rule. I'm going to take this index of 5 and divide it into 15. And it goes in there beautifully, nice and evenly. So I get -2 to the third power, which is -8. Remember, this is an odd root, so I can have a negative answer. All right, so then let's look at example 2. Now we're going to rewrite the radical, or rewrite the power in radical form. So as soon as you see that you have a decimal, you want to think of it in terms of a fraction. If you don't know what fraction 0.2 is, you want to read that decimal correctly. So if you read it correctly, it's not 0.2, it's 2/10. So I have W to the 2/10. 2/10 reduces to 1/5. And then to put that in radical form, it would be 5 radical W. For part B, we have a negative. So because of that negative, we are immediately going to put this over 1, and then this whole power is going down the denominator. So we get 1 over W to the 5/8, and now I can put that in radical form. So pause the video, put it in radical form. Okay, so in radical form, it would be 1 over the 8th root of W to the 5th. Because I cannot divide 5 by 8, this cannot be reduced. However, the problem is, remember, we cannot have a radical in the denominator. So some of your answers, you may see it left like this because at some point they quit rationalizing the denominator. But if we were to rationalize this denominator, which is what I want you to do, we have to figure out, well, I need to make a perfect 8th underneath here, and I only have 5 W's. For this to be a perfect 8th, so I can take the 8th root, I need 3 more W's to make 8 W's. So I'm going to multiply this by the 8th root of W to the 3rd. Because when we multiply like bases, I can add those exponents, and I'll have W to the 8th under there. What I do to the bottom, I have to do to the top. And so I end up with the 8th root of W cubed up top over the 8th root of W to the 8th. And so now I'm going to take my index here and divide it into the 8. So now when I divide it, it goes in there beautifully. And I have the 8th root of W to the 3rd all over W. And that is the properly rationalized radical form of W to the -8/5. All right, so then example 3, you're going to rewrite in exponential form. So go ahead and pause the video, put it into exponential form, and then restart it. Do both of these. All right, so in exponential form, we're going to take the same base, which is x, and then in the fraction, the index goes in the denominator, and what the base is raised to goes in the numerator. If you could reduce the fraction 3/4, you would. You can't here, so that is your final form for that one. Look at B. So B, remember that this is no different than if the y here were to the 4th power. So when you convert it, you have y, and then it's raised to the 4th power, and the index is 5. So 4/5. So then we come to some really fun word problems. Well, really it's just one word problem with a whole bunch of questions. So let's go ahead and look at Kepler's third law of orbital motion shows how you can approximate the period P, which is in Earth years, it takes a planet to complete one orbit of the Sun. So the function P equals d to the 3/2, where d is the distance from the planet to the Sun in astronomical units, which are called AUs, where d is the distance from the Earth to the Sun. All right, so if Mars is 1.52 AUs from the Sun, don't get hooked up on the AUs, think of it as miles. It's not really, but think of it as miles. 1.52 miles, then it won't bother you. So if Mars is 1.52 AUs from the Sun, how many Earth years does it take Mars to orbit the Sun? So we are going to use this formula here, and they have just given us, remember, distance, or d is the distance from the planet to the Sun. So they're telling you Mars is 1.52 AUs from the Sun. So that's that distance from the planet to the Sun. So here we go. We've got P equals, and instead of d, we're putting in the 1.52, and we're going to raise this to the 3/2. Now, of course, I'm going to allow you to use a calculator on something like this, because clearly you're not going to be able to figure out what that was. So if you put that in your calculator, it is going to give you approximately 1.87, that's a 7, Earth years. So I would assume on this particular problem you'd be using a calculator. Then part B says, find the length in Earth years of a Venusian year if Venus is 0.72 AUs from the Sun. So we're just going to use the same thing. So pause the video, plug it in, get your answer, and then restart the video. So again, we're going to use P equals, and the distance that Venus is from the Sun is 72 hundredths AUs to the 3/2. So if you plug that into your calculator, you're going to get approximately 0.61, so 61 hundredths Earth years. And then finally, part C, find the length in Earth years of a Jovian year if Jupiter is 5.46 AUs from the Sun. So again, pause the video, plug that into your calculator. You're just plugging and chugging stuff. All right, so this is what you put in your calculator. And it should have given you approximately 12.76 Earth years. Wow. Okay. So then we're going to look at example 5. I'm going to make that one really big. All right, so this time we're going to find the product or the quotient. So we can only multiply the same radical to the same radical. So right now I cannot multiply a square root to a fourth root, but what I can do is convert this to its exponential form, convert this to its exponential form, and then we're going to have like bases. So the square root of 3 becomes 3 to the 1/2 times the fourth root of 3 becomes 3 to the 1/4. Again, the index here is 2, so that's why 2 is here. 3 is raised to the first power, so 3 to the first. The index here is 4, so there's a 4 here in the denominator, and 3 is raised to the first power, so 3 to the first. So now I'm multiplying like bases, so I'm going to add their exponents. So 3 to the 1/2 plus 1/4. If you don't cook and you don't know what 1/2 plus 1/4 is, which is 3/4, then you're going to have to find like denominators. The like denominator should be 4, so I would have to multiply 2 by 2 to get a 4, and that means I have to multiply the numerator by 2. So I end up with 3 to the 2 plus 1 over 4. 2 plus 1 is 3. So 3 to the 3/4. And then I'm going to convert that back into its exponential form, which is the fourth root of 3 cubed, and we know what 3 cubed is, so we can multiply that out to 27. We cannot simplify, I just put the wrong root on there, so fix that. The fourth root. So I cannot simplify the fourth root of 3 to the third because I only have 3 3s. I don't have 4. So it's not a perfect fourth. Nothing's going to come out in front. So that's why we're going to multiply 3 times itself 3 times to get 27. All right, so for part B, now we're dividing like bases, but we don't have like radicals. So again, let me make this big and straighten it. Good enough for government work. Okay, so again, I'm going to convert this to its exponential form and this to its exponential form. So we get the square root of x cubed is going to be x. Square root means there's a 2 in the denominator, and x is raised to the third power, so this becomes x to the 3 halves over. X is my base. It's a cube root, so I've got 3 in the denominator, and x is raised to the second power. Now we are dividing like bases, so we subtract the exponents, but you want to subtract where there are more. Since 3 halves, which is 1 1/2, is bigger than 2/3, we want to subtract up in the numerator. So all of these are going to subtract up here. Now I need to have like denominators. If you multiply 2 times 3 together, you get 6. So I'm going to make both denominators 6. 2 times 3 is 6, so I have to multiply the top up here by 3. And then 3 times 2 is 6, so I have to multiply this numerator by 2 as well. So I end up with, all right, so I have x to the 9/6 minus 2 times 2 is 4/6 over 1. So we don't normally write things over 1, so you won't see me continue that part. So, but you end up with x to the 5/6. And now we have to convert that back to radical form. So I get the 6th root of x to the 5th. All right, for part C, we're going to do the same thing. Because we don't have the same radical index here, we cannot multiply them together. Even though they both have a 7, you have to convert them into the radical form. So the square root of 7 is going to be 7 to the 1/2 times the cube root of 7 is going to be 7 to the 1/3. So the least common denominator between 2 and 3 is 6. So I have to multiply 2 by 3 to get to 6. So the 1 gets multiplied to 3. The 3 here gets multiplied to 2, and so the 1 gets multiplied by 2. So I end up with 7 to the 3/6 plus, because I'm multiplying like bases, I can add those exponents, 2 6. So I get 7 to the 5/6, and so it looks very similar to the previous one, except for instead of an x we have a 7. And so to rewrite that in radical form, I've got the 6th root of 7 to the 5th. Normally I would make you multiply out 7 to the 5th because it's an actual number and you can, but I'm not going to make you do it here. If you had a calculator I would, but so let's look at example 6. So for example 6, you're going to write each in simplest form. So these are a little bit different because this base can actually be converted if you prime factor it. Remember, 32 is made up of 5 2's. So that's how you're going to end up simplifying it. It's a whole lot easier. I mean, you could convert this to its radical form, but it's actually easier to use the fractional exponent because you'll see why here in a minute. Now we do have a negative. So the first thing I'm going to do is put this over 1, and we're going to take this whole power and put it downstairs in the denominator. So take the reciprocal. So 1 over 32 to the 4/5. Then I'm going to convert 32 into 2 to the 5th. So I get 1 over, instead of 32, I have 2 to the 5th. And actually, I don't want that in parentheses. So let me erase the parentheses. So I have 2 to the 5th. And then that's 32. So that is raised to the 4/5. And this is what's great about this. So I've got a power to a power, so I'm going to multiply exponents. 5 times 4/5, the 5s are going to cancel, and you get this really nice 1 over 2 to the 4th. And you can figure out what 2 to the 4th is, or you should know it already, is 16. So 32 to the negative 4/5 simplifies to 1 over 16. So you try B. So stop the video, try B and C. Remember for C to read that decimal out correctly to yourself and then restart the video. Okay, so I'm going to convert 16 into 2 to the 4th. And I'm going to raise that to the 3/4. Power to power, we're going to multiply these exponents. So if I multiply 4 to 3/4, the 4's cancel. Sorry about that announcement. Okay, so then if the 4's cancel, we end up with 2 to the 3rd, which is 8. So no need for a calculator. All right, so for C, if you read that decimal correctly, it's negative 3 5/10. So I'm going to deal with a negative first by changing it to 9 to the positive 3/5, and then 1 over 9 to the 3 1/2, or 3 5/10 is 3 1/2. Then we have to convert that to its improper form. So you get, 1 over 9 to the 7/2. And then I can change 9 into 3 squared. So 3 squared is my 9, and that is raised to the 7/2. Now you got power to a power. So the 2 times the 7/2, the 2's are going to cancel, and you end up with 1 over 3 to the 7th. And normally I wouldn't expect you to multiply that without a calculator, but I will do that for you, and that is 2187. All right, so on this last page, we've got a little bit more complicated on the inside here. So we've got a power to a power, so we have to multiply each one of these by this power. So we could take care of the fact that we have a negative exponent by putting this over 1. And we are going to take the reciprocal. So we end up with 1 over 8x to the 15th raised to the positive, erase that, to the positive 1/3. Then power to power, remember that this has an exponent of 1. And so I have 1 over 8 to the 1/3 times 15 times 1/3 is 5, so x to the 5th, so 5. And 8 can be converted into 2 to the 3rd, and so that's raised to the 1/3 times the x to the 5th. And so I get 1 over 3 times 1/3 is 2, and then x to the 5th. Then for B, we have a mixture of fractional exponent and some radicals going on here. All right, so I'm going to rewrite this as 9, then the x, then the 4th root of y is going to be written as y to the 1/4. Then all of this is raised to the 3/2. And then my 9, I'm actually going to change the 9, because 9 can be written as 3 squared. So I'm going to change that to 3 squared. I'm just going to save myself a step. So then we've got power to power. So don't forget that this x is to the first power. So I'm going to multiply these powers to the 3/2. So we end up with 2 times 3/2. The 2's are going to cancel, so you're going to get 3 to the third. 1 times 3/2 is x to the 3/2. And 1/4 times 3/2 is, oddly enough, 3/8. So it's kind of ugly. So 3/8. So then we need to simplify this, and you can simplify it in two different ways. So you can either write it as 27, because 3 cubed is 27. Then you have the square root of x to the third times the 1/8 root of y to the third. That's a times right there. So that could be one answer. Or this could be, oh, well, this could be an answer as long as, hang on. So that could be an answer, or your previous answer would be fine because it's so odd, as long as you multiplied the 3 to the third out. So this is just an ugly, kind of weird question. So those are your two choices. Then C, I'm going to multiply power to a power here and here before I deal with the negatives. You could deal with the negatives first. You could switch these around, put the x in the denominator and the y in the numerator. Let's go ahead and do that. Let's do that first. So we've got y to the positive 1/3, and then x to the positive 2/3, and all of that is raised to the 15th. So now I'm going to do power to power. 1/3 times 15 is 5. So I get y to the 5th. And 2/3 times 15, 3 goes into 15 5 times 2 is 10. So I get over x to the 10th. These are not like bases, so you cannot subtract them. And that is it. Good luck with your homework. Let me know if you have any questions.